All right, ladies and gentlemen, to go with our whole acid-base idea, we know that when we put acids and base together, we make things called salts. And amazingly enough, depending on what salts are made from, they can act like acids and bases, and that makes complete and total sense when we start thinking about where they're coming from. So, we need to have a conversation for that. A salt, the word salt, is just another name for an ionic compound. And when they dissolve, they break apart into ions. And so if that happens, then the catch is, under certain conditions, they can behave like acids and bases. If one of them accepts protons, they're a base. If one of them is willing to donate a proton, they're an acid. So we know that's part of the catch here. So hydrolysis is the idea or the ability of a salt, an ionic compound, when dissolved in water, to generate H plus or OH minus because they dissolve. So their ions can help generate more H plus or OH minus from the water. So conditions. Condition 1, neutral solutions. So salts that consist of anions of strong acids and cations from strong bases have no effect on pH, and we know that. We know why. Strong acids produce weak conjugate bases, and strong bases produce weak conjugate acids. So if they're weak conjugates, they're not going to be easily accepting or donating. And so we don't have a problem there, and we know things are neutral. So, for example, SA is a conjugate base, and it has no affinity for A. So the conjugate base here, the conjugate base of A minus, has no affinity for H plus. It doesn't want H plus. It doesn't really care. If it did want H plus, it would still be with H plus. SB, well, B it can't produce any more H plus. It doesn't have any affinity for them. So it's all good. So NaCl is an example because Na comes from NaOH, a strong base. Cl comes from HCl, which is a strong acid. And so because of that, NaCl, when dissolved in water, is always neutral. It just gives you no effect on pH at all. So that's one condition. If you have salts that were created from strong acids and strong bases, you are going to have a situation where there is very little effect on the pH, okay? But we can have a basic solution if we have a base coming from a weak acid, because remember, weak acids produce strong conjugate bases. So if that's the case, then they are going to make solutions seem basic because they will rip the H plus from water, creating OH minus. Therefore, you have a basic solution, okay? So example here, we have NaC2H3O2. All right, this is the deal. Na probably comes from something. But C2H3O2 comes from a weak acid, acetic acid. And because of that, this guy becomes a strong, I'm sorry, let me go back. So that guy's a weak acid. Because it comes from a strong, a weak acid, that means the conjugate base is stronger. So it has more of an affinity for the H, okay? So it's not acid, but it would be basic because it's a conjugate of a weak acid. So how do we figure it out? Well, we do ice tables. Here we go. So we've got this going on right here. So how do we figure all of this out? What's happening? Well, we know we know this. I keep moving backwards and forwards. Sorry about that. We know this guy. Oh my goodness, my pin's not up. That's my problem. Okay, so we know what this guy is. We know all about him. We even know something about his Ka. His Ka is right here. So if we wanted to find the Kb of this guy, what would we do? We'd go right here and we do this calculation. We take 1.0 times 10 to the negative 14th. Sorry, it's hard to write. And 1.8 times 10 to the negative 5th. And we divide them and we'd come up with a number. And when we came up with that number, we'd get a Kb of 5.56 times 10 to the negative 7th. Okay? So that's a little bit greater than water because water is 1 times 10 to the negative 7th. All right? So we know it's a little stronger than water. So now we go in and we say, okay, so we figured that out, right? We figured the KB out. We know what that is. So you have to set up the ice table. So here we have the ice table. Oh, I'm sorry. Go back. Ice table. So we know we have 0.5 molar to start with. We have nothing here that we're going to use because it's liquid. We know we have 0 and 0. Here we're subtracting x, right? I'm going to put a line down here, okay? We're adding x. I'm sorry, adding x. All right, so here's 0.5 minus x, and this is x and x. So everybody with me so far? So we basically now have our ice table. Then once we have our ice table, we will set up an equation. I'm going to go up here at the top to set up the equation, okay? We have 5.56 times 10 to the negative 7th is equal to x squared over 0.5 minus x. We're going to negate the x, so we're not going to use the x at all, okay? Because times 10 to the negative 7, it's so small. So we end up solving that x is equal to 5.27 times 10 to the negative 4th. So that is the POH. That is the POH. So if we go to the POH, then we figure out, or I'm sorry, yeah, that's the concentration of the OH. So then we plug that in and we figure out that the negative log of that number, 5.27, EE negative 4, and we get 3.27 as our POH. So our pH, remember, pH is 14 minus 3.28, and we get 10.72. So this is basic. So when we put sodium acetate into water, it's a basic solution because the acetate comes from, it's the conjugate base of a weak acid, okay? So calculate the value of the pH of 0.3 molar NaF solution. The Ka for HF is, okay, that's going to be really important for us, right? So bottom line for any salt, I'm sorry, I should have copied that down and I didn't. Okay, so it's the same problem. So what I'd like you to do is I'd like you to try to solve that problem on your own, and you're going to bring that back to me tomorrow with a solution. All right, so bottom line, for any salt whose action cation is neutral, properties and those anions a conjugate base of a weak acid, the solution will be basic. So acidic solutions, a couple of ways. Salts in which anion is not a base and the cation is a conjugate acid of a weak base produce acidic solutions. So the opposite is true. If we have a weak base, then we're going to have a conjugate acid that's stronger. Therefore, the salt will produce acidic solutions. So salts in which anion is not a base and the cation is a conjugate acid of a weak base. Here we go. We've got this one right here. Okay, so ammonium chloride. We know that NH3 is a weak base. So that means the conjugate acid of a weak base is a stronger acid. So we need to find out, right? So here we go. Set up ice. There's the ice setup for you. We see what that is. We solve. Sorry, go back. We solve by putting this in. This is the Kb value, so we have to solve for the Ka value. Okay, so we have to solve for the Ka value for that. And we do that by taking 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. Right, and we get and we get 5.56 times 10 to the negative 10th, okay? And then we use that, and we use that to solve. So we now know that 5.56 times 10 to the negative 10th is equal to x squared over 0.1 minus x. That's so small, so we're not going to use that. So that means we now have 5.56 times 10 to the negative 10th times 0.1 Okay, and we're going to take the square root of that answer, and we get a concentration of, we get X is equal to 7.46. So that would be the OH value, or no, the H value. That would be the H value, right? Because we're talking about a conjugate acid. So that would be the H value. So you take negative log of 7.46, and you get a pH value of negative 0.87. Okay? That seems a little bit strange, but oh no, you know, I forgot something. Hang on. That's not right. That's not right. Let me erase that. I jacked it up. I jacked up the calculation. Forgot something. So don't panic. No panicking here. Okay. So negative log of 7.46. Negative 6. I forgot to put the exponent in, and that's what I get. I get a pH of 5.1. That is more appropriate. Okay, so it's not super acidic, but it is on the acid side. It's less than 7. Okay, so if both are conjugates of weak acids and weak bases, then you must look at which one is stronger. So if the Ka is greater than the Kb, then the salt is acidic. If the Kb is greater than the Ka, then the salt is basic. So we just have to compare the Kas and Kbs, and if you're given something, you have to calculate. Okay. So another way to get an acidic solution is if you have a highly charged metal cation, it'll rip OH from one of the waters. So if you have something that has a high charge, the higher the charge, the better it happens, the greater the acidity of the metal cation. So, and this is what causes yellow pit stains in shirts. So this happens a lot, okay? So that's it, guys. Thank you so much.